kind of need to summarize what is stretching and shrinking. And so basically that happens if you are multiplying by a constant. So adding a constant, we saw shifted the entire graph up, down, left, right. If I multiply by something on the outside, so if you see, like, if you want to summarize this, c times our function. Okay, we said outside is y and it does what it says. So it's like taking all of your y values times that number. So if it is bigger than 1, it'll stretch it vertically. If it's between 0 and 1, it will shrink it. Negatives do something else, so we're not into those yet. So if you multiply by a number on the outside, outside changes y, does what it says. So it's like taking all of your y values times that number. If the number is bigger than 1, it causes your graph to get taller and skinnier. If it is smaller than 1, we are making our height shorter, so if you get a shorter, fatter graph. Think of it kind of like stretching a rubber band. Now, if I take a rubber band and stretch it up, it's going to get tall and skinny. If I push it down, it gets shorter and fatter. Everybody should probably be jotting down something from this slide, because I doubt you guys just know all this on the top of your heads. And this picture just shows us an illustration. It's a black one here. Was my original, and when I took it times number bigger than 1, it got taller. And this one, the black's the original, when I took it times something smaller than 1, it got shorter. Horizontal is similar. It's caused by when we multiply by a number, but we know if something is horizontal, where is that number going to be? Inside or outside? Inside. So inside changes the x, and it does the opposite of what we think. So, so if you have a number on the inside, so you have a function, and inside that function you are multiplying by c. That is a horizontal stretch or shrink. But it does the opposite. So if the number is bigger than 1, it actually shrinks. And if the number is between 0 and 1, it stretches. The horizontal stretching and shrinking can be a little harder for people. So when we go through it, I'm going to kind of show some different options. With all the stretching and shrinking, if you struggle, your best bet is to actually write out the ordered pairs from your parent function and think about what changes. If it's changing if it's on the outside, it's going to change our y, and it does what it says. If it's inside, it changes our x, and it does the opposite of what it says. So let's take a look at an example. I'm still expecting parent functions. How many exact points for a parent function? 3. And how do I have you show that it's a parent function? How do I know which is which on your graphs? Right, first one's solid, the second one is solid. On the Math Excel, I know you can't necessarily do that, but on any test quizzes, that's the expectation, and that's what we're doing on all of our homework problems and class examples. Okay, so let's say I asked you to graph g of x equals 2x cubed. What's my parent function? The chair. X cubed is our chair. So let's draw that. If you know that it's a chair, you don't have to have a ton of points, just 0, 0, 1, 1, negative 1, negative 1. Now that's not enough to know the graph for sure, but if you know it's a chair, that's enough to go from there. Outside is y, and it does what it says. So this is saying times 2. What that's doing is taking the y values times 2. If you struggle with that, you can write your points. You do not have to. This step is optional. But outside, y does what it says. So if I look at these points, the x won't change. What's 0 times 2? 0. Okay, x doesn't change. 1 times 2. X doesn't change. Negative 1 times 2. Negative 2. So you might be able to just strictly do that from your graph, and that's fine. If not, write those points and change your y. So now I have my graph, and I can see it's a vertical stretch. I stretched it out so it got skinnier when I did that. If I said 1/2 x cubed, so it's the same parent function. It's on the inside now. So is it changing my x or my y? X. So, if you think about your points, this will change my x, but it's the opposite of what it says. So it says multiplying by 1/2. What would be the opposite of multiplying by 1/2? Dividing by 1/2, which is the same as multiplying by 2. All right, so when I think about this, I'm doing the opposite, so I'm really taking all my x's and I'm going to multiply them by 2 instead. So 0 times 2 is still 0. 1 times 2 is 2. Negative 1 times 2 is negative 2. So we have 0, 0, 2, 1, negative 2, negative 1. So this one was a horizontal stretch. You took that original graph and you stretched it sideways, which caused it to kind of flatten a little bit and get wider. I want you guys to try the third one. Okay. We're struggling a bit. Most of you graphed the correct parent function, but some of you, your points that you wrote down for that parent function were not correct. The absolute value of 0 is 0. The absolute value of 1 is 1. What's the absolute value of negative 1? So those are my points, and you can do more if you want. Writing out the points is totally optional, but it gives us a visual for what's happening to our graph. 2 is the outside. Does outside change x or y? Y. And outside inside does what it says. So I'm taking all of these times 2. So x doesn't change, y times 2. So we get 0, 0, 1, 2, and negative 1, 2. So then we can see this is a vertical stretch. It made our graph get skinnier because you're basically holding that bottom and stretching the sides up. All right, we definitely need some more of these still. Let's look at this one. So we're going to do it all on the same graph. We have a cube root of x, we have a cube root of 3x, and we have a 2/3 cube root of x. What does my cube root graph look like? A chair, but kind of flattened, right? Turned on its side. So the cube root of 0 is 0. Cube root of 1 is 1. Cube root of negative 1 is negative 1. Now that's certainly enough if you know what your graph's going to look like. If you don't, if you get confused between the x cubed and the cube root, you could always do more. If you did more, what would be the next x value you could put in? 8. And the cube root of 8 would be 2. So you could have 8, 2, and negative 8, negative 2. So we see it's like the chair flipped on its side. Okay, so there's my original. Now, for the first one, the cube root of 3x, is that 3 inside or outside? Inside. Which variable does inside change? The x. So I'm going to change my x, and it does the opposite of what it says. So it's telling me to multiply by 3. What's the opposite of multiplying by 3? Dividing by 3. So I'm going to take each of those x's and divide them by 3. So 0 divided by 3 is still 0. 1 divided by 3 is 1/3. Negative 1 divided by 3 is negative 1/3. I plot those. 0, 0, 1/3, 1, negative 1/3, negative 1. If you did more, if you had 8, it would be negative 8/3, negative 2, and positive 8/3, positive 2. So we can see this is a horizontal shrinking. It's like I took my ends and I shoved them towards each other. So that forced it to get kind of taller when we did that.
How did you get to dividing by 3?
Inside, we always do the opposite. So just like yesterday, if we were adding on the inside, we moved it in the negative direction. So anything on the inside does the opposite. So opposite of multiplying by 3 is dividing. Other questions? Okay. Let's do the other one. So again, if you don't need to write out the points, you don't have to write out the points. But it can be helpful. If I look at this one, the 2/3 is on the outside. So does it change x or y? Y. Outside is y, and y does what it says. So I'm going to take those and multiply them by 2/3. So 0 times 2/3 is still 0. 1 times 2/3 is 2/3. Negative 1 times 2/3 is negative 2/3. 0, 0, 1, 2/3, negative 1, negative 2/3. So this one was a vertical shrink. And our graph gets shorter. Practice everything together. The final thing that we can do with our graphs is reflecting. If it's on the outside, it's making your y's negative. So if you think about a graph, if you make your y negative, it reflects across the x-axis. So a negative on the outside will reflect or flip our graph over the x-axis. If it's on the inside, it's changing the signs of our x, so it will reflect our graph across the y-axis. So negative on the outside, reflect over the x. Negative on the inside, reflect over the y. So if I ask you to sketch the graph of f of x equals negative x squared, what's the parent function? Parabola. 0 squared is 0. 1 squared is 1. If you wanted to square it is 4. Negative 1, 1, negative 2, 4. Okay. This is on the outside. Outside changes the y's, and it does what it says. So if I'm making my y's negative, which axis does this flip over? The x. So I'm just taking a point and flipping it down. So this one's at 2, positive 4, so we go to 2, negative 4. Negative 1, 1, go to negative 1, negative 1. Negative 2, negative 4. So my final graph looks like that, just an upside down graph. That's why I bring it. All right. What if I give you one where the negative is on the inside? So if I said square root of negative x. Okay, what's the parent function look like? Except it's a square root, not a cube root. So can we have the negatives? No, it's just like the positive half of that. So the square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. If you want another point, you could do 9, 3. If the negative is on the inside, what does it reflect over? It's just taking my x values and changing their sign. So instead of 4, 2, you would have negative 4, 2. Instead of 9, 3, you'd have negative 9, 3. So it's going to look like this. So that's all of the individual transformations. Now we're going to start mixing them together. So we'll look at problems with multiple transformations. Are there any questions so far? Go to this. So my function, I have negative parenthesis x minus 2 cubed plus 1. All right. So there's a lot of different things going on here. Let's kind of make a list of the different transformations. What will the negative out in front do? What will the minus 2 do? Inside is x, it does the opposite. So the subtracting from the x will move it in the positive direction. And what's that plus 1 do? Okay. So my parent function, x cubed. 0 cubed is 0, 1, 1. negative 1. If you wanted more points, you could do 2, 8, negative 2, negative 8. That's not required. When we do these, it is important to do the up and down movement last. Because you notice it's kind of separated. The negative has to happen. We have to flip before we move our graph up. Okay. So let's take a point 0, 0. If I flip this over the x-axis, does it go anywhere? No. Then I need to move that point right 2 and up 1. If I take 1, 1, if I flip it over the x-axis, it goes down here. And then I have to move that point right 2 and up 1. Okay, if I wanted 2, 8, if I flip that over the x, it goes to 2, negative 8. Right 2, up 1. If I take negative 1, negative 1, if I flip that over the x, where does it go? And then we move it right 2 and up 1. And if you had it negative 2, negative 8, if you flip that, it goes to negative 2, positive 8. Right 2 and up 1. So my graph ends up like this. Are there questions? Let's try some more. Okay, so let's figure out all the different transformations happening here. What does the 1/2 do? So vertical shrink. It's on the outside, so it changes y, so it's vertical, and it does what we think. What does the +2 do? Okay, what's the -3 do? Parent function, the square root. So square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. If you wanted another one, you could do 9, 3. Alright, I'm going to do this once without writing out the order pairs, but if I lose you, I'll go ahead and write out the order pairs like I was doing on our other stretching and shrinking problems. So, the vertical shrink, it's like affecting my y, it does what it says. So if I take my y times 1/2, if you're at 0 times 1/2, it's still 0. And then I move that left 2, down 3. Alright, if I take 1, 1, if I take my y times 1/2, the height is now 1/2. Left 2, down 3. 4, 2, my y value is 2. If I take that times a half, it's now 1. Then left 2, down 3. If you had 9, 3, your y value is 3 times a half, will be 3 halves, or 1 1/2. Left 2, down 3. So we get the same shape, it's just a little flatter. If you struggle doing that, you can certainly write out points. Okay, first thing you did is take your y's times a half. So that gives us 0, 0, 1 1/2, 4 1. And then could you take those points and move them left 2 and down 3? So if the stretching and shrinking confuses you, you can write out the points for that and then do your final transformations for them. Okay. Why don't you guys try one? Here is your 3 times 2 plus x squared plus 1. Does it matter that it's 2 plus x instead of x plus 2? I mean, addition can happen in any order, so that's the same as saying x plus 2. So, parent function transformation. It is quite beautiful. All right, so everyone had our parent function. Make sure you have at least 3 exact points. Then, this 3, it's outside. So it changes y, it does what it says. So this is a vertical stretch. What's the plus 2 do? And the plus 1. Okay, so I'm taking my y value times 3. So it's currently at 0. Times 3, it's still 0. Then left 2, up 1. Okay, this point has a y value of 1. Times 3 is now at 3. Left 2, up 1. Okay, this point, if you did it, has a y value of 4. If you take that times 3, you're now at 12. You guys probably didn't go that far, but left 2 and up 1. Okay, this says a y value of 1. Times 3 is now at 3. Left 2, up 1. Can you tell what we have now? It is a much skinnier parabola that's been shifted over. Okay, make sure, again, minimum of 3 exact points there. I am stopping here today. We are working on this again tomorrow. I'm not teaching anything new, we're just practicing it some more. There's a Math Excel assignment open, but you'll notice it is not due until Thursday. So tomorrow we're going to do some more class examples. We're going to do a little practice with groups in class tomorrow, and then you'll have some time to work on the Math Excel as well. But you should get started on it. Don't just assume you're going to have a whole class period tomorrow, because you will not. So Math Excel.